Statistics 3, central limit theorem. Type 1, standard error of the mean. B, finding the sample size. So in this question here, we can see that we're told that the population is normally distributed. So it doesn't matter what the sample size is, we know that our central limit theorem is going to apply. And we can see that we're given the population is got a mean of 12 and a standard deviation of 3. So we have to find the sample size. That's what we're looking for in this question. And we're given the probability where x bar is our sample mean. And we're told that the probability that the sample mean is greater than 12.5. So if we're looking for n here, the first thing we note is that it is normally distributed. And we can see that mu is equal to 12, our population mean. Our standard deviation is 3. The sample mean that we're looking at to test is 12.5, and we don't know what n is. So we're going to be working backwards here in this question. So we're given the probability that the sample mean is greater than 12.5. And of course we can't find that from our tables because of course we're given sample mean here. So we need to write that probability in terms of z. But of course we need to work out what is z first of all. So therefore let's sketch what this looks like. So in other words, what is the z-score that we're trying to find that gives us a probability of 0.05. So if I sketch that normal distribution curve and I'm getting 0.05, so it's quite small, so it must be greater than that value. So we're getting a very small value. That shaded bit is 0.05, in other words the probability, the area under the curve. And we're looking for what is this z-score here. Now we know we can't find that from our tables. So again, what we know is that if I look at less than that z-score, I'll get all of this green shaded area. And the green and the red together makes a probability of 1. So therefore, if I subtract the green area from 1, I'll get the red area. In other words, if I look at the probability that z is less than or equal to z1, well then that's the same as getting 1 minus 0.05. So in other words, 1 minus 0.05 is 0.95. So now what I can do is I can actually go to my tables. Well, let's just add in my tables there. So my tables, again, I go to page 36, 37 of my maths tables. So this image here is showing all of them in one, whereas in your maths tables it's spread out over 2 pages. So I have to look for 0.95. So I'm going along and I'm looking for 0.95 from my tables. And I have 0.9505, or I have 0.9495. Now, basically, that is 5 below and 5 above. So it's actually smack bang in the middle of these two values. So in other words, if I go across there, I'm going to get Z1 must be 1.645. Okay, so if it's exactly halfway between, we have to go halfway. If it's closer to one or the other, we go with the closest one. But in this case, it's 0.1645. Okay, so that's my unknown. So now what I can do is I can use my standard error of the mean. Because of the central limit there, which is that z is equal to x minus mu over sigma over root n. And again, this is page 35 in our maths tables. So we've just worked out that z is 1.645. Our sample mean is 12.5. Our population mean is 12. and our standard deviation is 3. And what we're trying to find is n. So we're going to try and isolate n on its own. So of course, if I multiply both sides, if I turn my fraction upside down and I multiply, well, I have 12.5 minus 12, which is 0.5. And turning my fraction upside down and multiplying, I get root n over 3. And now I want to get root n on its own. So multiply across both sides by 3 and divide across both sides by 0.5. And then to get n on its own, I'm going to square both sides. So if I square the left, I'll get n. And if I square the right, well, I'm going to get n is approximately equal to 97.4. And of course, we take the closest value because n is always going to be a sample size. So n is an element of the natural number. So that's something that's going to be important to remember. Okay.